Okay, it looks like we have quite a good group here. I will get started. So, hi everyone. My name is Jennifer. I am the marketing specialist here at the Energy and Geoscience Institute here at the University of Utah. I wanted to welcome you to our spring webinar series. So we usually have 3 webinars in a series. Today is the first one. Today we're going to be hearing from Dr. Tony Doré, and he will be doing his presentation on Pangaea, assembly and fragmentation of a supercontinent. I will put in the chat the link to where you can register for the other webinars coming up next month and the month after. So sit back and enjoy. And everyone, this is Dr. Tony Doré.
Okay, so Jenny, can you give me an indication as to whether you can see the screen okay?
I can see it okay.
All right, I'm going to go into presentation mode then. I hope to go into presentation mode. Yes, here we go. Now, how does that look?
That looks great, Tony.
Okay, thanks very much. Well, thank you everybody for coming to this first of EGI's spring webinars. Just to introduce myself, I'm Tony Doré, and I used to work for Equinor back in the day. After retiring from Equinor, I joined EGI as a kind of consultant. I revel in the title of Global Chief Scientist. Well, that in fact means I advise on projects, and I'm currently resident in London, so I'm kind of EGI's European representative, you might say. But as you probably know, this meeting's being hosted from Salt Lake City. So my title today is Pangaea, Assembly and Fragmentation of a Supercontinent. And you're probably wondering what's that got to do with the global energy mix. And the honest answer is not much. For this first webinar here, we're having a bit of fun talking about the supercontinent of Pangaea, but there will be a lot of energy in this talk, I can tell you. I want to thank my co-authors, people that helped me with this presentation and have been engaged in new research on Pangaea. Eric Lundin of Equinor and Albina Gilmelina at the University of Bergen in Norway. Both of those are in fact resident in Norway. Now, I'd like to say this is a picture of what the hostile interior of Pangaea might have looked like in at the end of the Permian, beginning of the Triassic, but of course we can't do that. This is in fact a picture of Canyonlands, not too far away from Salt Lake City, where EGI is situated, but it gives quite a good proxy for what Pangaea might have looked like at the time of its acme, you could say. So let's talk about Pangaea. We all basically know what Pangaea was. Basically, about 250 million years ago, the continents came together and were more or less all joined up, largely because of the fusion of this lump down here, Gondwana, South America and Africa and so on, with this northern piece, North America, Asia and Europe and so on. And not to forget the sort of docking around about the same time of Siberia onto the Baltic Shield to form the Urals. So that's a very simplified picture of Pangaea. And today I'm going to talk about several things, all basically featuring some aspects of new research. Firstly, I want to ask, how well established is the supercontinent cycle? And I'll say more about that later. I want to talk about the reasons that this supercontinent was hit by such massive volcanism during its brief existence. And then I want to talk about how Pangaea broke up and what the relevance of that might be to deep water margins that we see today. Then, time permitting, at the end, I'd like to talk about some aspects of what Pangaea was like and what the effects that might have had on the environment. So here's another even more simplistic picture of Pangaea. So on the left-hand side, what Pangaea, the supercontinent, looked like 250 million years ago, and of course the configuration of the continents today. And people basically talk about the supercontinent cycle, that this conglomeration of continents wasn't the first time this happened, and basically it all breaks apart to form the present day configuration. Sometime in the future, maybe 250 million years, it's said these continents might come together to form another supercontinent, which some people call Amasia. And then there's the idea that way back in the mists of time, back in the Precambrian, there were other supercontinents with names like Nuna and Rodinia and so on. So I want to have a look at that supercontinent cycle. But, you know, what did Pangaea really look like? Was it just this congealed lump in the middle of the world ocean? Well, here's a more accurate map of Pangaea. And what you can see from this immediately, and this is titled, What Did Pangaea Actually Look Like? Is that Pangaea was kind of a little bit stringy. You know, you could travel from where I am in London right now to Salt Lake City, I guess, without ever leaving continent. And of course, they were much closer together because there was no Atlantic in the way at the time. For that matter, you could travel all the way from Arctic Siberia, never leaving continent, and get all the way to Antarctica. So yes, a pretty impressive conglomeration of continents. But in other respects, this continent was already starting to come apart. So these pieces of continent over here were never part of Pangaea. These are pieces of continent that later coalesced to form mainland China and part of Southeast Asia. And you can see there's this great big ocean biting into Pangaea. And this, of course, is Tethys, the remnants of which are seen in the present-day Mediterranean. And in Tethys, you can see that this new ocean, Neo-Tethys as it's called here, is forming, and little pieces of Gondwana land are basically breaking off and moving northwards, and they will eventually fuse with these terrains up here to form China and Southeast Asia. So basically that's what Pangaea looked like. And now I want to show a very different picture of how we might envisage Pangaea. So this diagram takes a little bit of getting used to. So bear with me for a moment while I explain what it means. This is an idea that Eric Lundin and myself developed from a sketch by Daly in 2018, Mike Daly, who used to be president of the Geological Society. So on the bottom horizontal axis here, we can see geological time going back to 600 million years ago, all the way through to the present. On the vertical axis, we can see the relative area of the different continental pieces, which are shown in these colors here. So this vertical axis, it represents relative area. And in the middle of here, you can see where all the continents are together as Pangaea. So a point I want to make about this is Pangaea didn't just suddenly come together. All the continents didn't suddenly merge. It happened over a long period of time. First of all, these two pieces of Gondwana land merged together in something called the Pan-African orogeny. And this was about 550 million years ago. In other words, 300 million years before the existence of Pangaea. And some people call Gondwana a supercontinent because, after all, this green piece here consisted of Australia, Antarctica, South America, and Africa. The next event towards the formation of Pangaea happened here 400 million years ago, and this was the Caledonian orogeny, when parts of the Baltic Shield started to merge with Laurentia, in other words, North America, to form the Caledonian orogeny. And only then, after Laurentia and Gondwana finally merged, do we actually get Pangaea. So my point here is that this wasn't a sudden coming together. It happened over a very long period of time. It happened over 400 million years. Another remarkable thing about this diagram here is actually right here. Pangaea in itself is a remarkable event in geological history. The present day configuration of the continents more spread out than they've ever been in the entirety of Phanerozoic history. That is right back to here, back to the Neoproterozoic, when the first multicellular life forms were starting to develop. So the present day continental configuration is unique in Phanerozoic geological history. That's something to think about. So how do we know how these continental pieces fitted together? Well, if you go back to the Jurassic, as far as the Jurassic, say about 200 million years ago, it's relatively easy because we can see the age of the ocean floor. These blue colors here in these white ellipses are basically showing Jurassic age ocean floor, and then the youngest ocean floor is being formed here at the mid-ocean ridges. So we can basically pull all these together, and we know pretty much how the continents fitted together. But before that, it gets a little bit more difficult, doesn't it? Because here's the Jurassic. How do we know what was going on back here? Well, we haven't got any ocean floor older than about this. So we relied on other factors: fossil assemblages, similarity of fossil assemblages between continental pieces, paleomagnetic work, magnetic polar wander, and so on, and the ages of orogenic belts. So if you see a similar age orogenic belt in two pieces of continent, you can make a reasonable postulate that were originally stuck together. But if you go back to here, 550 million years ago, then we beyond this, further back from this, we don't even have any fossils to go on. So depending essentially on increasingly murky evidence of paleomagnetics and the age of orogenic belts. So there might have been supercontinents before this. Certainly the continents were clustered together in various configurations. But were they supercontinents on the scale of Pangaea? I think that might be a bit doubtful. And it might also be doubtful as to whether these pieces are eventually going to come together to form another supercontinent. So you hear a lot about the supercontinent cycle, and my point here is that it's not a slam dunk. The way the continents behave and the configuration of the continents through time might be a bit of more of a chaotic process than just a simple in-out cycle. Here's yet another version of this map in which I've put some more information. So I've added to this extinction events, large igneous provinces, and climate, with temperate shown here in green, cold in blue, and extreme heating events in red. And the point I want to make about this is that although Pangaea is often described as a hot, hostile continental interior, in fact, just before Pangaea, it was actually very cold. We were in an ice age, particularly affecting the southern hemisphere, and this took place at the end of the Carboniferous and the beginning of the Permian. But that didn't last too long in geological terms, because round about here, at the acme of Pangaea, at the end of the Permian, beginning of the Triassic, we had the biggest magmatic event in the history of the globe, at least in the known history of the globe. And this was the formation of the Siberian traps, during which 83% of the genera on Earth became extinct, and more than 90% of the species. And that wasn't all. In fact, Pangaea got hit by, towards the end of its existence, by another major volcanic event, and this is the Central Atlantic Magmatic Province, or CAMP, when again 73% of the genera became extinct. And somehow after that, life managed to rebound, because we all know life was very prolific during the Jurassic, which I guess is a testimony to the resilience of organic life. So let's have a look at these big volcanic episodes which hit Pangaea, because this is very interesting. So I'll go back to this map again. And this conglomeration of continents was hit by some of the biggest volcanic events in Earth's history. It starts basically 300 million years ago with the Skagerrak Large Igneous Province, which was a major magmatic event which affected a large portion of Scandinavia and a large portion of northern Britain and Scotland. Then in these pieces of China over here, Tarim and Emishen, we have two more major volcanic events, large igneous provinces. Particularly this Emishen here was a particularly huge event. But that was dwarfed by this one, the big daddy of them all, the Siberian traps, 252 million years ago, which, as I said earlier, was the largest volcanic event that we know about in Phanerozoic history. And this was really a catastrophic volcanic event. And there's some evidence there was another large igneous province at about the same time down here in Gondwanaland in Patagonia. And then at the end of the Triassic, this is this CAMP, Central Atlantic Magmatic Province event 200 million years ago, which many people think is intimately associated with the formation of the Central Atlantic and the Gulf of Mexico. So why was Pangaea hit by so many catastrophic volcanic events? Well, the easy answer that some people will give you was that this supercontinent was targeted by mantle plumes, which basically came from the core mantle interface and basically caused these huge volcanic outpourings. So a little reminder about mantle plumes. So this is the idea of mantle plumes, that hot columns of heated mantle rise up from the core mantle interface and result in massive outpourings of lava on the surface. And just to sort of note about what that distance is from the core mantle interface, 2,900 kilometers. That's about the distance from where I'm sitting now to the other side of the Atlantic. So that's a pretty huge distance. But there's no doubt that these things exist, and the classic example is Hawaii, of course. So present-day Hawaii is shown here on this bathymetric map. Is not the only representative of this mantle plume. We basically see a whole series of old versions of Hawaii now submerged, going back on the seamount chain all the way back to here. And basically this represents the plates moving over the top of a plume which is fixed relative to the lithosphere, relative to the overlying crust. And this basically goes back some 150 million years until these old versions of Hawaii are finally disappearing into the trench around the margins of the Pacific. So that's what a mantle plume should be like. So how did that match with what was happening in Pangaea? Well, the Pangaean large igneous provinces have something in common. The effect was very intense. There were high intensity magmatic events, and they happened over a very short period of time, 1 to 3 million years. Nothing like that example I showed you earlier. And there's little or no evidence of an incoming or outgoing hotspot trail. So what caused these events? Was it really mantle plumes, or could something else be causing the Pangaean magmatism? So one possible answer to this comes via this diagram here. So I'm showing you here another simplified picture of Pangaea created by Nikishin and his co-authors. This basically shows, again, a simplified sketch of Pangaea. But what it shows is what was probably the case is that Pangaea was surrounded by subduction zones. Now, subduction zones, a reminder, is where the oceanic crust is cooling and gradually sinking into the mantle, often at the margin with a continent, to form this thing called a subduction zone. And these slabs are basically descending underneath the lithosphere. So a couple of things about this. The first thing is, as this slab subsides, it creates a low potential area into which the continental crust can move. You can regard it basically as the continental plate being sucked into the subduction zone. And that's basically a process called slab rollback. And a lot of people think this is one of the main driving mechanisms of plate tectonics. So just as Pangaea had formed, it basically already had the seeds of its own destruction built into it, because it was being pulled apart by slab rollback forces. That's the first thing. Second thing is that the entirety of Pangaea will be underlain by subducted slabs. First of all, from this Appalachian Variscan belt, which is where Gondwana and Laurasia join together, there will be slab remnants underneath there. There'll be slab remnants underneath the Uralian fold belt. And all around with these encircling subduction zones, there will also have been descending slabs. So perhaps that had something to do with this intense magmatism that we see. And I'm going to say more about it in a minute. But the two takeaways from this slide are: Pangaea contained the seeds of its own destruction by subduction slab rollback forces, and there was a slab graveyard beneath Pangaea, and that might be implicated in the large igneous provinces. Well, okay, that's an interesting idea, but why should slabs actually create that massive volcanism? And To illustrate that, I'm going to point you in the direction of a rather fantastic YouTube video, which a friend of mine drew my attention to a while back. And this is produced by a unit called Deep Dive, and its title is "Why China's Largest Volcano is So Unusual." So this is a picture of Mount Changbai in eastern China, and it's one of the most impressive and destructive volcanoes on Earth, and it's created reasonable amounts of havoc during human history. And it's one of a series of volcanoes in interior China, which don't seem to have any kind of hotspot trail associated with them, but are the sites of intense volcanism. And they're a long, long way away from this Pacific subduction zone, which you can see running down the margins of Japan and up north to Sakhalin. So what it turns out basically is that if you look at that subduction, the subduction in some places is actually diving down deeper and deeper into the mantle, as most people think subduction zones do. But in this particular area where we have this volcanism, the slab is actually flattening out. It's flattening out at 600 kilometers approximately, which is the boundary between the upper and the lower mantle. And that's what we basically see underneath this volcanic area. Now, here's the general idea. On the top left here, the diagram, we can see what you might call a normal subduction zone, where the subducted slab goes all the way down and perhaps goes all the way down to the core mantle boundary. But in this particular case, in eastern China, it's actually flattening out at a much shallower level to form a stagnant slab at 600 kilometers. How do we know that? Well, we know it from a process called seismic topography, where we can basically map the density of the rock units with depth. And this is slides are jumping about a bit. I'm obviously too fast on the trigger here. These blue areas here are areas of high density, and you can see essentially evidence of this flattening out slab underneath eastern China. And the idea is that this slab subducted slab contains a lot of hydrous minerals which start to dewater at that depth, producing huge amounts of water, which lowers the melting point of the upper mantle and causes this intense volcanism that we see, what they call a big mantle wedge here. And the authors of this video here are saying, yeah, well, this is probably what we're seeing in eastern China, but point to some other areas where I also agree with them that we have this flat slab magmatism, the Franciscan magmatism of North America, Western North America, and the Alpine foreland volcanism of Europe being an example. So what we might be talking about here is not a plume coming from 2,900 kilometers down from the core mantle interface, but we might have a much shallower, a more temporary plume coming from a more shallowly buried stagnant slab. And the producers of this video go on to say that occurrences, these very quick and very intense occurrences like the Siberian traps here and also the Central Atlantic magmatic province may actually be attributed to this cause. So the proposal here is that the Pangaean large-scale magmatism and breakup might be attributable to the structure of the supercontinent itself rather than an external agency. In this case, mantle plumes coming from 2,900 kilometers down. Okay, I've talked about the supercontinent cycle, but I want to talk now briefly about another cycle, which you may have heard of, the Wilson cycle. And this is basically an idea that says, a testable idea that says, you start out with a continent, it starts to stretch, it starts to rift, eventually it forms an ocean, then that ocean starts to close with the formation of subduction zones, closes more, and then eventually it fuses together into an orogenic belt or a mountain range, but that's inherently weak and starts to rupture and starts to stretch, so eventually we get an ocean forming again in the same place. Well, does that apply to Pangaea? Oh, this is a diagram that I made to illustrate this on the right-hand side. And all these colored pieces here are the different parts of Pangaea, northern Pangaea in this case, that join together. And what we see here basically is that as Pangaea starts to break up, this is during the Permo-Triassic, yes, the rift zones more or less follow the old orogenic joints, more or less. So the rift zones are shown here in these orange dashes, and the continental pieces are shown in the different colors. So yes, it starts to stretch and starts to break where the old continental joins were. But if we look at that a little bit more closely, and this is the Northeast Atlantic. Northeast Atlantic was the original model for the Wilson cycle. By the way, this is Professor Tuzo Wilson, who proposed this idea in the 1960s. He was a geophysicist, a Canadian geophysicist. And he asked the question, did the Atlantic close and then reopen? How's this original question looking? Well, here's a picture of the North Atlantic on the right-hand side. And these pink zones here are the old orogenic welds. Sorry. These pink zones here are the old, jumping about a bit, sorry, are the old orogenic welds. And so what we can see here is that the Atlantic, which is shown in these colored stripes here, these are the different ages of oceanic crust, it didn't exactly follow these old continental joints. In fact, a large chunk of Laurentian crust, that's North American crust, was left behind, forming the what is now Scotland and Northern Ireland. In the case of the Labrador Sea and Baffin Bay, it appears that a new ocean formed through area of craton that apparently doesn't contain any continental join at all. So the answer to the question, how is Wilson's original question looking, is probably close, but no cigar. Is not a perfect fit. But to find out why the Atlantic should have broken up where it did, the North Atlantic, we have to look at how it was put together in the first place. So this is a picture of Laurentia, that's the North American piece, and Baltica, that's the European piece, coming together. And what we observe with these reconstructions essentially is that through time, the Baltic part moved northwards relative to the Laurentian part. In other words, there's a huge amount of lateral offsets and the development of huge shears down the middle of this origin. So we didn't just see a straightforward collision, we saw a sinistral shear, a left lateral shear. Now, if we look at the Central Atlantic, the Central Atlantic is often put forward as an absolutely perfect example of the Wilson cycle. And people, in fact, in the literature, people talk about this part of the Atlantic opening and closing like a concertina. So was it really like this? Well, superficially, it looks good. The Appalachian mountain chain here, which represents the original joining together of these two continental pieces, it's pretty well parallel to the present-day mid-Atlantic ridge, so it suggests that it might be. But in fact, that wasn't how the collision took place. Now we're going back in time to when Laurasia and Gondwana are about to collide, and this is back in the Paleozoic. This is 250, 300 million years ago. And what we can see here is that the North American piece and the South American piece are actually facing each other. And as these two continental pieces come together, we can see South America moving southwards relative to North America, sliding in a right lateral or dextral way, like this, until finally it arrives down here. So we've got a huge amount of lateral or shear motion going down this orogenic belt, this Assyrian orogenic belt. And there's evidence of this right lateral motion all over the place. If you look in the Appalachians and so on, you can see abundant evidence of this massive shear taking place. So the bottom line here is that it wasn't really a concertina, more like cutting cards. In other words, continental transform zones were strongly implicated in these orogenies, and they were the things that broke up to form the present-day oceans. So what we are therefore interested in is, if this is the case, if we actually have these lithospheric zones of shear, what would be the implication if you opened one of these rather than stretched an old mountain range and stretched it and stretched it and stretched it until it finally broke? Well, the answer might be a more sudden and more abrupt breakup process. And that's in fact what we see in the North Atlantic. The first example that I showed you, you see a very abrupt transition from continent into ocean, continent shown in yellow, ocean here in gray, with very little preceding extension. And even more extreme in the Central Atlantic, we see a rapid transition, a little bit of extension, but not much, and then a very rapid transition into ocean crust. So this is not a gradual stretching, it's a rather abrupt process. And I can do no worse than to read out this quote from Mutter in 1990, he was a great oceanographer who wrote, "The transition from clearly continental to a region with no continental character is completed in 20 kilometers. It's as if the continental lithosphere that was broken was extraordinarily weak." So what we're interested in, and what Eric Lundin, myself, and some co-authors were interested in, is what would be the implication of a breakup along one of these continental shears. Well, what we notice is, if we look at a couple of the end member margin types of Pangaea oceanic margins, is in some cases we see stretching, gradual stretching until the continent is so thin that eventually the mantle starts coming up and exhuming and becoming serpentinized. And that's the situation we see between Iberia and Newfoundland, for example. But in this example below, a magma-rich margin, we have a rather sudden transition from continental crust to oceanic, and the development of lots of volcanism, including these seaward dipping reflectors, or SDRs, which basically represent subaerial lava flows and intrusions, and the formation of flood basalts and so on. So many cases, when you hear people talking about magma-rich margins, they'll again assume this is because a mantle plume happened to impact this margin at the time of breakup. But another possibility we're looking at is if you open a subvertical shear in the lithosphere, then you might, and that transition, that opening is quite abrupt, you might create very large lateral temperature gradients because of the upwelling of the asthenosphere between these two pieces of lithosphere. And that might in itself cause melting. And that is not a new idea. That idea was suggested by Mutter again back in 1988. But we wondered if it could be applied to this idea of breaking up along a continental shear. So basically, we tested that in a recent paper, and this is basically the concept shown here on the left, which is you have a zone of continental shear, one of these zones of lateral motion, and basically it opens rather abruptly, convection is created, and that creates a volcanic margin. And we thought, okay, it's a great idea, but let's test it. So we tested it with computer modeling of the same sort of idea to the left. And I won't get into detail about this computer model on the right, but what I will say is that we managed to simulate the formation of an abrupt margin, these brown areas here, forming representing the continental crust. And these white lines here are geotherms, showing the geotherms rising to the surface, which also suggest the possibility that we could have associated magmatism. And we published that idea back in 2022 in the Geological Society. So, this is the only time in this presentation I'm actually going to say anything about petroleum. Those of you who are still interested in petroleum exploration might be interested in this because these are, so again, on the left-hand side, some margin types, the magma poor margin, stretch margin, I mentioned earlier, the magma rich margin. I've added transform margins here, where we basically have lateral movement in the present day between the oceanic crust and the continental crust. We've recently seen some major discoveries offshore Namibia, but also offshore Guyana and Suriname, where we see a rather unusual thing happening, which is that we are seeing discoveries in basin floor fans overlying what appears to be thoroughgoing oceanic crust, shown here by these seaward dipping reflectors. And that's something that people actually thought could never happen. But these recent discoveries, Venus and Graph of Namibia, seem to show that that is possible. And so the question then is then becomes open as to how do these margin types here result in what we see on the right? Are certain types of margins more prone to the development of petroleum systems, source rocks, reservoirs, and so on over the top of oceanic crust? Right now, it looks like magma-rich margins may be the most likely, simply because they were subaerial and shallower for a longer period of time, perhaps allowing the thick source rocks and reservoir rocks needed to form. But we don't know that that's the entire story. Transform margins might be implicated too. So EGI is currently working on an ultra-deep water plates project to try to investigate this. This next slide is simply an unashamed plug for that project, which we're currently engaged in, to try to find out what are the common factors in these ultra-deep water discoveries. What margin types do they preferentially occur on, and where else might we find those? If you want to find out more about that, please contact Rasul Sokabi at EGI. So finally, for my last few slides, I want to talk a little bit about a piece of research that we've been doing on some of the effects of the Pangaean intraplate magmatism, or these magmatic events that blitzed the Pangaean supercontinent. On the right-hand side, there's a rather beautiful diagram by Mike Benton of Bristol University, and I won't go into this whole thing, but bottom line is, particularly associated with the development of the Siberian traps, we had terrestrial mass extinction, a lot of the plants died, disturbed landscapes, soil erosion, increased continental weathering. Put all those things together and you have the potential for huge amounts of sediments to be delivered down into the margins of Pangaea, and also lots of soluble chemicals, of course, going into the sea, causing a process called eutrophication. So basically, this was devastating, not just for the land, but for the sea. I want to illustrate that. Excuse me while I take a drink. With reference to the to this area, the Greater Barents Sea. Now, this is a piece of continental shelf north of Norway, and you can see it's quite close proximity to the epicenter of the Siberian traps. And these are a couple of east-west profiles across the Barents Sea. And I want to draw your attention particularly to this grayish unit here, the Havert Formation. This unit basically is the earliest Triassic and formed in just 1 million years. It's thousands of meters thick. To put it in perspective, this was 1 million years. All the rocks above it were deposited in about 150 million years. So you can see what a sort of a catastrophic event this was. And here's some work done by Albina Gilmelina, who's kindly invited me into a project on this. Where she actually looks at sediment flux associated with this this catastrophic event. So you can see here on the left-hand side, sediment load per year on the vertical axis, time on the horizontal axis, and you can see this enormous peak at 250 million years ago, when basically that was the time of the Siberian traps, and the discharge 50% bigger than any modern river. And it's also illustrated in the right-hand side of this figure here. So that basically at the bottom, those purple stripes are the earliest Triassic discharges, and the orange things that the orange bars here that you can see are essentially the discharge rates of modern river systems. And you can see this continues far on to the right, far in excess of modern rivers. And here are some diagrams made by Albina, which basically show how this happened. And this is the Greater Barents Sea here. And here we see the earliest Triassic delta migrating across the Barents Sea, forming what eventually can probably be described as the largest delta in the history of the world. And such that by the late Triassic, this delta covered the entire huge area of the Barents Sea and was discharging into the rest of the Arctic. And we can see the signal of these sediments all over the Arctic. And that was basically that was basically published not so long ago in a paper which was placed in the Journal of the Geological Society. I'm very pleased to say won the paper of the year, and Albina was also recently named Young Researcher of the Year by the Geological Society. So I'm very proud to be associated with this work. One of the things the question we're asking now is the end Permian increase in sediment flux observed worldwide? We see this massive discharge of sediments in the north, close to Siberian traps. What about the rest of the world? Well, it turns out that if this paper at least is correct by Algeo and Twitchett 2010, that this increase is seen in lots of other areas. So basically, this shows a bunch of areas around Pangaea, and the blue columns represent the sediment discharge just before just at the end of the Permian, and the pink color here represents the earliest Triassic discharge. And you can see this massive increase is reflected in lots of areas, even when the sediments are carbonate, not clastic, which is interesting in itself, perhaps a boost in productivity due to that eutrophication process I talked about earlier. Interestingly, if you get further away into near Tethys down here, although the sediment rate wasn't high, we don't see such a strong signal. And in the oceanic domains, or Panthalassa over here, again, we see, if anything, a decrease in sedimentation rate. So that basically opens up the question, is this increase in sediment flux something we can see everywhere? Can we see it in Gondwana in the southern hemisphere? Indeed, can we see the extinction event so clearly in the south? We don't know the answer to that question, and we're currently looking into it. If anybody has any ideas on that, I'd be extremely pleased to hear them. So, winding up, here's my conclusions. Firstly, the supercontinent cycle, a simple model of repeated coalescence and dispersal in out, is probably not the reality. It's probably more chaotic and less simple than that. Pangaea contained the seeds of its own destruction. Slab rollback, creating breakup, and numerous flat-lying slabs, creating magmatism. The Wilson cycle, the opening and closing of oceans, is still applicable, but with some important modifications. We think that continental transforms with major lateral movement were strongly implicated in both continental assembly and breakup. Many of the Pangaean margins are blunt, they're abrupt. Of continental shears. Breakup along these lithospheric shears might be implicated in the formation of volcanic margins, and the margin types are probably critical to identifying the modern ultra-deep water petroleum plays. Pangaean permatriassic extinction event also included a massive increase in sediment flux to the margins, and it's exemplified strongly in the Greater Barents Sea, those examples I showed you. And then lastly, a question: how widely reflected is this massive increase in sediment flux, and indeed the extinction event on a global scale? And as I say, I'd be very interested to hear people's ideas on that. So I want to leave you with this slide, which is a rather beautiful slide I discovered cruising through the internet. This is a political map of Pangaea, where the present-day countries would have been on Pangaea. And who knows that if in another 250 million years the continents finally fuse together again, perhaps we'll again see this kind of political unity. So that's the end of my talk, and I'd be very pleased to hear any questions that you might have.
Tony, we have a few questions in the chat, one from Albert and one from Alan. Are you able to see the chat box at the bottom?
Yeah, okay. Okay, do you see the main ophiolites forming in the same age period? Example of such ophiolites is the Oman one. The yeah, okay. By the same period, I don't know whether you can put your sound on, Albert. Do you actually mean during the acme of Pangaea, 250 million years ago, 250 to 200 million? Is that what you mean?
I'm trying to unmute.
Yeah. Okay. So it looks like we can't get sound from that, but can people speak on this, Jenny?
Yeah, they can. You can
Yeah.
unmute yourself or
Well, my answer to the question is, of course, there will be ophiolites. But for those of you who are not ophiolite fans, that basically means big subducted lumps of mantle and sorry, abducted lumps of mantle and ocean floor thrust up into mountain ranges. Well, of course, we see those during the existence of Pangaea, because after all, it was formed by the coming together of continents which create ophiolites. I'm not actually sure about the Oman one, but so I'm not going to commit myself to that one until I take a look at it. Moving down from Alan Scardina, I can't, let's see. Namibia discoveries. These are usually attributed to the excellent Apto-Albian source rocks. How does your proposed model allow those early margin source rocks to mature to oil expulsion late enough that the hydrocarbon are trapped, rather than maturing too early due to high heat flow? Well, actually, that's precisely the question that we're, thanks for, it's a great question. It's precisely the question that we're looking at in the deep water story right now. We want to examine that. And that means we need to do geohistory model. But a superficial answer to that would be, look, on a volcanic passive margin, you start out with shallow water, because we know the seaward dipping reflectors were formed subaerially. So basically, you will be more proximal to the source, and you will get thicker source rock and reservoir rock development. That's the first thing. Second thing is, it then needs to be buried by more sediments coming in over the top of it. So we basically need a fairly continuous sediment supply to get this timing that you're talking about here. Now, I would say that that would be a doubtful occurrence in a magma pore margin, a highly stretched margin like the Iberia one, because it becomes too distal to form thick enough source rocks, thick enough reservoir rocks, and ultimately have a thick enough overburden to cause maturation. That's essentially precisely the question that we're looking at now. What about intermediate margin types? Yeah, and if you'd like to, if you can put sound on, I'd like to know whether that was a decent enough answer.
Yeah, that was. Can you hear me okay?
Yeah. Okay.
Yeah.
Thank you.
we can hear you.
Oh, okay. So yes, so that's a good answer. But when I was leading the charge to get Shell into Namibia, we had huge debates about this exact question and whether or not some of the apparent carbonate-looking features were really shallow water carbonates or volcanics or some combination of the two, and how all this worked together in terms of timing and seals. And having left the project after entry, I haven't kept up on the details, but it's still been a question that's bothering me.
Yeah. Yeah, and I think the answer might be somewhat different in every place. So if we look at Guyana, Suriname, for example, where we also think that some of the hydrocarbons are over the top of oceanic crust, there you've got a rather complex interaction between a transform margin and a volcanic passive margin. And it's these intermediate cases we're particularly interested in. What's exciting is whether we can actually identify these in other areas apart from those two well-known recent discovery examples.
Thank you.
I'm looking at some other looking at some other questions here. Melanie Pling, sorry, I believe is at Bergen. I have a question about the mantle plume in Hawaii. You said it disappears at the plate contact. Does that possibly mean the origin of the mantle plume is related to a subduction zone and in fact did not develop under the oceanic plate? Do you know if there's any research done? Well, remember that what's going down the subduction zone, Melanie, is a fossil oceanic mantle plume. It's not the mantle plume itself. The mantle plume is currently underneath Hawaii. So, you know, so what's disappearing down the subduction zone is 100 million years old. But the relationship between subduction zones and mantle plumes is a whole massive subject. And offline, I can refer you to some of the discussion on that, because, you know, in fact, I'm thinking of something right now. But rather than go into that very detailed subject, I will find you some material on that. Any more comments or questions? Melanie, do you want to come in and qualify that question a bit? Because I sense I didn't give you a particularly good answer.
No, I think it's good. I watched the documentary you spoke about in your talk. Yeah, so that was very interesting.
Oh, did you see the one on the flat-lying slabs?
Yeah, the one from in China, is it? The China to Korea border, yes.
I think this talk is being recorded, so those of you listening in have another chance to see it. And one thing I would certainly recommend is that you watch that video. I hadn't, that YouTube, I hadn't known of its existence until a friend pointed it out, but it's been extremely influential on my thinking. In other words, massive volcanism in the middle of continents doesn't necessarily have to be a classic mantle plume. It could be a much shallower kind of plume from a flat-lying slab. Any more comments or questions?
Let's see, I don't see any more in the chat at the moment. Okay. Do we want to wrap up, Tony?
Sorry?
Or do we want to wrap it up? Oh, wait, I think we have, oh, it looks like Alan has another message to you directly. I'll send that to you, Tony. Well, it looks like we're done here. Is that right, Tony?
Yes, well, I just want to thank you all I want you to thank you all for coming in, and also particularly because this wasn't a talk on modern day energy sources and the modern day energy mix, but the next two EGI seminars definitely are going to be about that, so don't miss those. Do you want to say a little bit about what they are, Jenny?
Yeah, so our next one coming up, everyone, is April 4th at 9 a.m. Mountain Time. That is also a Thursday, and that's going to be presented by Dr. Carlos Vega Ortiz. He's a carbon research scientist here at EGI, and his presentation is going to be on petrophysics, geochemistry, and data science, enhancing geomodeling and source rock analysis. And in the chat at the very top, I did put a link to where you could register for that seminar or the webinar. So please tune in for that one. Tony?
Okay. Well, thank you very much, everybody. And those of you in North America, have a good day. And those of you in Europe, have a good evening.